Welcome back to the chemical quantities video series. We're still on the mole, but I misspoke in the last video. This is not the last video, but this is not really part 3. We're going to call this an interlude, and this interlude is going to be on two topics: molar mass and molecular formula. The molar mass of something is simply the mass of 1 mole. When dealing with chemicals, we frequently call this the molecular weight, or the molecular mass, or the atomic mass, or the atomic weight, or the molar mass. I tend to use molecular weight, which is abbreviated MW. Go to the periodic table and you'll find something that looks like this: the box with the element symbol, the name, the atomic number, and the atomic mass. And to this point, the unit for the atomic mass has been atomic mass units. Now, the atomic mass unit is not a real weight, it's actually normalized, because 1 AMU equals a really small number, 1.662 times 10 to the minus 24th grams. That's really, really small. So we say it's 1 AMU to make it easier. So a carbon atom that has a mass of 12.01 AMUs, if you multiply it by the mass of 1 AMU, you get just under 2 times 10 to the minus 23 grams. Still an unbelievably small number. So let's take an exceedingly large number, like a mole. If we multiply the actual mass of a carbon atom times 1 mole of carbon atoms, and yes, I know you have 6.02, but remember it's a measured number. I want one more significant figure here, and you get 12.02 grams per mole. That looks really, really close. As a matter of fact, that's off by approximately 0.1%. So we can now say the molar mass of carbon is not 12.011 AMU. We get rid of the AMU and we replace it with grams per mole. So the molar mass of carbon is 12.011 grams per mole. Grams per mole is the label for molar mass. You can do this with any element. Go to the atomic mass, which used to be an AMU, and change it to grams per mole. Doesn't matter what the element is, change the AMU to grams per mole. You now have the molar mass of that element. And it's truly that easy for the elements. Let's switch topics a little bit, and then at the end I'm going to combine the two. Take a typical molecule, in this case the water molecule. You can write it out this way, but that's a pretty simple molecule, and molecules can get more complicated. Here's a molecule of caffeine. Looks a little bit more complicated than the water, but molecules can be even more complicated. This happens to be vitamin B12, and there are lots of molecules out there that are even more complicated. And you don't want to have to write these structures out every single time we're going to talk about a molecule. So what we do is we talk about the molecular formula. Molecular formula is simply an inventory of the elements that are in a compound. For example, for the water molecule, we have 2 hydrogens, 1 oxygen, and so we would write the molecular formula you're very familiar with, H2O, where a subscript goes to the element to the left of it. For the caffeine, it turns out that you have 8 carbons, 10 hydrogens, 4 nitrogens, 2 oxygens. So you would write the molecular formula like this. Last but not least, for our examples, you have vitamin B12, which happens to have 63 carbons, 88 hydrogens, 1 cobalt, 14 nitrogens, 14 oxygens, and 1 phosphorus. So its molecular formula would look like this. Now, the molecular formula does not tell you how a molecule is constructed. For that, you need what is called the structural formula, which, cleverly enough, tells you how the molecule is structured. For example, suppose you had a compound with this molecular formula. The molecular formula simply tells you have 3 carbons, 8 hydrogens, 1 oxygen. And it turns out there are 3 ways to put these together. Each way is a separate chemical, so we'll have separate physical properties. So for example, you could have this structure, which is called 1-propanol, and it has a boiling point of 97 degrees Celsius. This structure is called 2-propanol. All we've done is move the OH from here to here. Different chemical, different boiling point, 82.6 degrees Celsius. But it turns out that the third way of putting it together is this way. Totally different, no OH component. This is called methoxyethane, and it has a boiling point that is way lower than the others. all have the same molecular formula, all have different structural formulas. These are known as isomers, iso, the same molecular formula. So isomers simply have the same molecular formula, but different structural formula. Now we're going to combine these two interludes of molecular weight and molecular formula so that you can figure out what the molecular weight is of a molecule. Now there is an old chemical saying, I don't know which wise old chemist said it, the whole is the sum of the parts. And to show you that you know how to do this, we're not even going to start with chemicals. We're going to start with Legos. Now it turns out that an individual blue Lego weighs 2.24 grams, an individual white Lego weighs 1.76 grams, and an individual red Lego weighs 1.16 grams. So if you put 3 blue Legos together, what should it weigh? Remember, the whole is the sum of the parts. What are the parts? 3 blue blocks. Each block weighs 2.24 grams. So when you multiply those together, you get 6.72 grams. So I predict that this will weigh 6.72 grams. We put it on the scale, and it weighs 6.73 grams, which is only 0.1% away. For a high school lab, that's pretty close. What if we mix them up? We have this structure. What's our prediction as to the mass of this structure? The whole is the sum of the parts. So you've got 2 blue blocks, each at 2.24 grams. 1 white block gives you 1.76 grams contribution. The 2 red blocks total up to be 2.32 grams. So when you add up each of the parts, you get 8.56 grams. You toss it on the scale, and once again, you're within 0.1%. So now here's one for you to try. What do you predict the mass of this structure will be? Stop the video and go. And I predict that this will weigh 14.88 grams. How? The whole is the sum of the parts. The 3 blue blocks weigh this much. 2 white blocks total to be this, and the 4 red blocks will donate 4.64 grams. Those are the parts. Add up the parts to get 14.88 grams. So that's what our prediction is. We toss it on the scale and we get 14.89, which is actually less than 0.1% away. Very, very close, well within experimental error. So if you can do this with Legos, you can do this with molecules. It's all based on the molecular formula. Example, water. It has a formula of H2O. How much does it weigh? Well, we have 2 hydrogens here and 1 oxygen. The whole is the sum of the parts. So we take the 2 hydrogens, multiply it by its molar mass to get this value, use the molar mass of oxygen to get 16.00 grams per mole, add the 2 of them up, the whole is the sum of the parts, and you get 18.016 grams per mole. But using correct significant figures, I would say that the molecular weight of water is 18.02 grams per mole. How about the methoxyethane? Well, it has a formula of C3H8O, and I have 3 carbons, 8 hydrogens, 1 oxygen, and I remember that the whole is the sum of the parts. Multiply the carbon by its molar mass to get its contribution, multiply the hydrogen by its molar mass for its contribution, the oxygen by its molar mass to get its contribution, sum up the parts, convert to correct significant figures, and you can now say that the molecular weight for this compound is 60.09 grams per mole. This will also be the molecular weight for the 1-propanol and the 2-propanol because they all have the same molecular formula. So here's one for you to do. Caffeine. Stop the video and figure it out, then come back. I'll give the correct answer, walk you through it, and then we'll be done. And the correct answer is 194.20 grams per mole. So we start here and come up with the correct molecular formula. Identify how much of each element we have. Remember that the whole is the sum of the parts. So we're going to multiply each element by its molar mass to get the individual contributions. Sum up the parts. We're incorrect significant figures. So we get the answer of 194.20 grams per mole. So to review this video, the molar mass is the mass of 1 mole of something. In this classroom, molar mass and molecular weight are totally interchangeable. To get the molecular weight of an element, just change the AMU to grams per mole. The molecular formula is an inventory of all elements in a compound. For ionic compounds, it is called a formula unit, but I'll accept a molecular formula no matter what. It doesn't tell you anything about how the atoms are put together. To do that, you need the structural formula, and you can have isomers which have the same molecular formula but different structural formulas. To get the molecular weight for a compound, the whole is the sum of the parts. Tally up the number of each element. Multiply each element by its molar mass. Add the parts together to get the molecular weight of the compound. So we do have one more video left in this series, and that's going to be how to do molar conversions with compounds.